Hello, geometry students. In this video, we're going to take a look at our 12.1 through 12.3 notes. And in Unit 12, this is where we're going to begin to study three-dimensional figures. So the first thing we're going to do is look at different ways to view three-dimensional figures, and one of those ways is called an isometric view of a three-dimensional figure. So an isometric view, I like to call it a corner view. It's looking at a three-dimensional object from the corner, which means you can view three entire sides. You can actually see three entire sides. If you look at this shape right here, we can see the top of this object. We can see what's called the front of this object. This view over from this direction we call the front, and we can also see this is called the right side of the object. So when you're looking at a corner of a three-dimensional shape, you can see at least three different sides. So what we'll be concerning ourselves with when we're looking at an isometric view of a three-dimensional shape, we'll be looking at the top view, the left view, the front view, and the right view. More on that in just a second. Another type of view is what we call an orthographic view of a three-dimensional figure, and I like to call this just a flat view. Okay, that's where you can only see one entire face. So in other words, imagine if you were a bug or something, and if you walked around to the front of this object and you were looking at it square on, all you would see would be this L shape, okay? So when you just see one flat surface, that's what's called an orthographic view. So let's take a look at an example where we're going to look at a description. We're going to draw an isometric view, and then we'll also look at the orthographic views. So this first description is a shape. It's a triangular prism that's 3 units high with two sides of the base that are 2 units long and 4 units long. So we're going to use this what's called isometric dot paper to help us draw that. So let's first of all get the height of this prism. So try and pick, right about in the middle here, we're going to just draw a segment that would be 3 units long to get the height of this object. So it might look something like this. Okay, so that actually would take up 4 dots in order for the segment to be 3 units long. So there's the height. And then we're also told that the base is 2 units by 4 units now. So triangular base. So let's draw one side of the base that's 2 units long. So that means you're going to cover 3 dots. Oops, I went a little too far. Hold on, let me fix that. Yeah, that's 2 units long, and then the other side of the base is going to be 4 units long. So it would look like that. Okay, and then we'll continue drawing. It's pretty sad when you can't even draw a straight line with dots to help you. Okay, I remember this object is 3 units tall. Okay. And then we will just finish the shape. And now you can start seeing that triangular prism. Now what we could do to make it look a little bit 3D is we could imagine it's a see-through prism, and so you can draw this back edge as well if you want. So we can see that we have a triangular prism. It has 2 triangular bases. The prism is 3 units long, and the base is one side is 2 units long and another side is 3 units long. So this is that isometric view. We're looking at it from the corner, so we can see 3 sides of it. We can see the top, we can see the front, and we can see the right side. So now let's go ahead and draw the orthographic views. And the 4 orthographic views that we're going to draw a top view, we're going to draw a left view, we're going to draw a front view, and we're going to draw a right view. So you might use this image that I put at the top of the notes to help you orient yourself on which view is actually the top, which is the left, the front, and the right. Okay, so imagine that you were a bird and you were flying above this triangular prism. If you were looking straight down on this, what you would see would be, you would just see this triangular top. So let's go ahead and draw that, and we're going to label it as well. The top would be a triangle. Okay, one side measures 2 units, one side measures 4 units, and then we don't know the length of that side. Okay, so now the left view would be, imagine if you could walk around to behind this thing and look square onto it, then what you would see would be, you'd see this rectangle, a rectangle that measures 3 by well, 3 by, we don't know this measure. So let's draw a rectangle. This is the left view. It's kind of like from behind. It would measure 3 units by something. We're not sure what that length would be. And then the front view would be if you were standing over here looking straight on, you would see another rectangle that measures 2 by 3. So we'll draw that rectangle that measures 2 by 3. And then the right view would be if we could walk around here and look square onto this, we would see this rectangular face that measures 3 by 4. So let's draw that rectangle and label it's 3 by 4. All right, so let's go ahead and take a look at the next one. We're going to draw another triangular prism. This one is 2 units high with 2 sides of the base that are 5 units long and 4 units long. All right, so we want to start kind of in the middle and kind of low. So let's make our 2 units high right here. So that's 2 units high. Now, one edge is 4 units long and one is 5 units long. So I'm going to draw the 4 units long edge this way. Say 1, 2, 3, 4. And the 5 unit long edge go in the other direction. 1, 2, 3, 4. 1, 2. Yeah, that's 5 units. Okay, and then we'll just finish the prism. Okay, and again, if you wanted to make it look a little bit 3D, like it were see-through, then you would add this back edge. Okay, so let's draw those same 4 orthographic views. We're going to draw the top, the left, the front, and the right. Okay, so if you were flying above, like a bird flying above this prism and looking down on it, you would see a triangular shape that has one side measures 4 units, the other 5 units, and we're not sure what this measure is, so we're just going to leave that unlabeled. So we have one side that's 4 units long, one side that's 5 units long, and then we're not sure about that third side. Okay, the left side would be, if you could go around here and look at the back of it, it would be a rectangle that is 2 units by whatever this length is, that again we don't know. So that's a long skinny rectangle that measures 2 by, we're not sure about that other dimension. The front would be, the front, let me erase that mess, sorry. The front would be this view, okay? If you were standing looking at this, you would see this rectangle that measures 2 by 4. So let's draw a rectangle and label its dimensions 2 by 4. And then the right side is if you were coming around this side and looking at this rectangle, and you'd see a 2 by 5 rectangle. So 2 by 5. Okay. How about this last example? This time we're going to draw a rectangular prism that's 2 units high, it's 3 units wide, and it's 5 units long, okay? So I'm going to draw the height first. So grab, let's see, I guess we could start right about here. Let's draw, I'm going to make it, hold on, I want to stay consistent with my color. Let's make it red. Okay, so here's our height. Now, it is 3 units wide and 5 units long. So if I go here, there's my length, my width of 3 units, and then let's do a length of 5 units. 1, 2, 3, 4, 5. Oops, I think I went 1 too many. Let me fix that. There we go. That's 5 units long. And then remember, this is a rectangular prism, so let's finish that by drawing the rectangular bases. Oops. Okay, and then again, if we want to make it look 3D, we could draw those back edges that wouldn't be seen if this were a solid object, so we'll pretend like it's a see-through object. Okay, so then let's draw those 4 orthographic views again. So we'll draw a top view, a left view, a front view, and a right view. Okay, so the top view, if you were flying above this, looking down, you would see a rectangular shape that is 3 by 5. So let me draw that shape, that 3 by 5 rectangle. Okay, the left view would be around to the back. You would see this rectangle that measures 2 by 5. All of these views are going to be rectangles, by the way. The front view would be this view, okay, this rectangle that measures 2 by 3. 2 by 3, and then the right view would be over here. That would be this rectangle that measures 2 by 5. 2 by 5. Okay, so the next thing we're going to do is we're going to go in the opposite direction. So this time we're going to be looking at some orthographic views, and we're going to translate those into a three-dimensional shape that we're looking at isometrically. In other words, we're looking at the corner. So this takes a little bit of practice, but I think the easiest place to start is let's start with this front L-shaped view. Okay, so I'm going to try and get an L shape. So it would look something like this. It needs to be 3 units tall. So I'm going to draw an L shape that's 3 units tall. Whoops, I think I made that 4 units tall. Let me fix that. Always count one too many. Okay, so now what I'm looking at is I'm looking at the L shape. There we go. So that would be my front view. I would see that L shape. Now, from the top, if I were looking up here looking down, I can see that it should have two rows of that L shape. So I'm going to go ahead and finish the first row. So it would look like this. There we go. And then I'm going to add a second row onto that. There we go. And then I like to shade the top view. I think it helps you get a little bit of the 3D effect. Okay. So now I think we've drawn it correctly, because if you look at the front, we'd see this L view from the front. Okay. From the top, we would see now this kind of bold line here shows you that there's different levels. There's different number of cubes piled up on these two. So we would see a rectangle from the top with that kind of break there. From the left, if you went around to the back, the left view would be just a 2 by 3 rectangle, and from the front, if you were looking square on, you would also see this 2 by 3 rectangle, but this bold line here just tells you that the depth is a little bit different. Okay, so you'll have some more chances to do that on your homework, and you'll get some more practice with that. And the next thing we're going to talk about with three-dimensional figures is we're going to talk about cross sections. So a cross section would be the intersection of a three-dimensional solid, like these pyramids, the intersection of a three-dimensional solid and a plane. Okay. Now, the shape of the intersection, that plane that's intersecting the three-dimensional shape, the shape of that plane depends on the angle of the plane. So consider the square pyramid below and determine the shape of each cross section. We can see how this cross section, if you imagine a plane that's slicing through this pyramid, that plane is parallel to the base. So since it's parallel to the base, it's going to take on the same shape as the base. It's called, this is a square pyramid, so that means that this cross section would take on the shape of a square. Okay. Now, if you were to tilt the plane a little bit, you can see now that the cross section isn't going to be a square anymore. It's a little wider down here than it is here, but these two sides are parallel, so that means it's taking on the shape of a trapezoid. And then if we tilt that plane even more so that it's perpendicular to the base, we can see that the intersection of the plane and the three-dimensional solid would be a triangle. Triangle. Okay, so in this next example, it says determine the shape of the cross section of a horizontal and a vertical plane. So let's make kind of sort of a little table here. So write down the word horizontal and then write down the word vertical, and we're going to determine what would be the shape of, let's see, oops, that's not how you spell vertical. Let me fix that. Vertical. There we go. Okay, imagine first a plane that would be parallel to the base. Well, if I slice this parallel to the base, then the intersection of the plane would take on the same shape as the base. So this first one's going to be a circle. Okay, but if I were to take a plane and slice it vertically, let me see if I can sort of sketch what this would look like. A vertical cross section would take on that shape, and hopefully you can tell what that shape would be. That shape would be a semicircle. So semicircle. Okay, all right, and the next shape we have a cone. If I were to slice horizontally, the intersection of the plane and the three-dimensional solid would be the same shape as the base, so it's going to be a circle again. Okay, but if I were to slice vertically, slice a plane through this vertically, then that shape would look more like this. Hopefully you can see that that vertical cross section would be a triangle. Okay, in the next example, in this cylinder, a horizontal cross section would take on the same shape of the bases, so it would be a circle. And then a vertical cross section would look something like this. Let me see if I can sketch it. It would look something like that. I think you can see that vertical cross section would be a rectangle. Whoops. Rectangle. And then last but not least, let's look at this triangular prism. I think you can see that a horizontal cross section would take on the shape of a triangle, but a vertical cross section, let me attempt to draw that, would look something like this. Okay, so hopefully you can see that that would be in the shape of a rectangle. So now let's take a look at the first of 4 three-dimensional shapes that we're going to study. The first one is a right prism. We will be looking at prisms, we will be looking at cylinders, and then pyramids and cones. And our goal for today will be to learn how to find the surface areas of these three-dimensional shapes. So let's start with our first one, a right prism. Okay, so a right prism, these three-dimensional shapes are called a polyhedron. That's just a shape with many sides. So it's going to be a polyhedron that has 2 congruent parallel faces that are called the bases. Okay, so if you take a look at this, let me grab a highlighter here. If you take a look at this three-dimensional shape, we have 2 polygons that are congruent and parallel, and those are the bases. The bases, there will always be exactly 2 of them, and they will be congruent and parallel. And then the other sides we call lateral faces, and you can see that those lateral faces would take on the shape of a rectangle. So the lateral faces, this shape has 6 of them, and they're all going to be rectangular. So a prism will have 2 congruent parallel bases, and then its lateral faces will always be rectangular. Well, hold on, let me spell this right. Let's spell rectangular lateral faces. All right, so let's talk about how to find the lateral area and surface area of a prism. First of all, lateral area would just be the areas of the lateral faces, so the areas of those rectangular faces. This is called a net of this three-dimensional object. So if we were to lay it out flat, you can see the 3 rectangular faces, and then here are the 2 triangular bases. There's exactly 2 of them. They're congruent and parallel. So the lateral surface area would be the area of the lateral faces only, and then total surface area is the area of the lateral faces plus the 2 bases. So let's start by deriving a formula for the lateral area for a right prism. So looking at this example of a triangular prism, if you look at each one of these lateral faces, you can see one of them measures C by H. This one measures B by H, so let's go ahead and label that height of H. And then the last one, the last rectangle, measures A by H. So if we were going to find the area, the total area of all those rectangles, we would just take A times H, the area of the first rectangle, plus B times H, the area of the middle rectangle, plus C times H, the area of the right triangle. I mean not right triangle, right rectangle, meaning the rectangle that's on the right side of these 3. Okay, now I want you to notice that all 3 of these terms have a common factor of H. So I'm going to factor that H out and rewrite this expression like this. A plus B plus C all times H. And now the reason I wrote it like that is because I want you to see that A plus B plus C, if I look over here at this picture, A plus B plus C is the perimeter of the base. So I'm going to take this A plus B plus C in our formula, and I'm going to replace it with a capital P, where that capital P represents the perimeter of the base. And then, of course, we will multiply that times the height. So to find the lateral area of any right prism, we just take the perimeter of the base and we multiply it by the height, okay? So LA will stand for lateral area. SA will stand for total surface area. So if I want to get the total surface area, then it would be the lateral area plus the areas of the two bases. So we're going to write it like this. Capital P times H, that's the lateral area, plus 2 times capital B, where capital B represents the area of the base. All right, so let's take a look at an example where we're going to find the lateral area and total surface area of this prism. Now, first of all, we need to realize what kind of prism this is. This is a triangular prism. Do you see 1, 2 congruent parallel bases? Remember, a prism does not always have to be sitting on its base. We know it's a triangular prism because I see 2 triangular congruent parallel bases, and then there's going to be 3 rectangular faces. So let's start by finding the lateral area. So to find the lateral area, we'll take the perimeter of the base times the height. Now, perimeter of the base would be the perimeter of this triangular base. Well, I know 2 of the 3 sides, but I don't know the 3rd side. Fortunately, this is a right triangle, so we can quick do the Pythagorean theorem and find out what that missing side is. Let's call that missing side C for now, since it's the hypotenuse. So that hypotenuse squared is equal to the sum of the squares of the 2 legs. Okay, so C squared would be 36 plus 25. C squared that adds up to 61. So C is the square root of 61. Okay, so that means that the perimeter of our base, and let me go ahead and write C is the square root of 61, then the perimeter of our base is going to be 5 plus 6 plus the square root of 61. So we will take 5 plus 6 times the square, times 5 plus 6 plus the square root of 31. I'm going to put all of that in parentheses, and then we're going to multiply that by the height. Now, the height of the prism isn't necessarily how tall it is. The height of the prism is the distance from one base to another. So you can see that these 2 bases are 7 centimeters apart, so it's 7. All right, so simplifying that a little bit, 5 plus 6 is 11, and then I'm going to distribute the 7, so I'm going to rewrite that as 77 plus 7 times the square root of 31. Again, all I did is I just added together the 5 and 6, and then I took 7 times 11 and 7 times the square root of 31. I'm going to put parentheses around all of that, and then write the correct units. Since we're measuring in centimeters and this is surface area, then our units will be centimeters squared. Okay, so we're halfway done with this problem because we have found the lateral area. Now let's find the total surface area. So to find the total surface area, I need to take the lateral area, capital P times H, plus 2 times the area of the bases. Well, we've already done this pH. We don't need to do that work again. So I'm going to rewrite 77 plus 7 times the square root of 31 plus 2 times, now I need to find the area of the base. The base is a rectangle whose base is 6 and height is 5. So 1/2 base times height, that would be 1/2 times 6 times 5, okay? And so simplifying that a little bit, let's see. 2 times 1/2 cancels, and then 6 times 5 is 30, which I can combine with the 77. So our final answer is going to be 107. Let's see, 107 plus that 7 times the square root of 31. Let's put parentheses around all that and put the correct unit, which would be centimeters squared. Okay, our next 3-dimensional shape that we're going to study and find the surface area of is a right cylinder. So a right cylinder, like a prism, has 2 bases. It's just at this time the bases are going to be always going to be in the shape of a circle. A prism can have a base that's any shape, but a cylinder will always have a base that is a circle. So a right cylinder will have 2 congruent circular bases, and I should have mentioned also, let's put a comma in, and also that, well, let's just add here, that they are also parallel as well. Okay, just like the bases of a prism are parallel, the bases of a cylinder are also going to be parallel. So we have these two circular parallel congruent bases, and then we have this curved surface area that would be the lateral part of the cylinder. So now let's talk about how to find that lateral area. So imagine if you would a soup can. If you were to take a soup can and cut it here and peel that label off and lay it out flat, that soup can label would be in the area of a rectangle. So how do you find a rectangle? You take its base times its height. So the base would be this measure right here. When we put it all back together, you can see that the base of this rectangle is also the circumference of the base of the cylinder, okay? And how do we find a circumference of a circle? We take 2 times pi times its radius. So this lateral area, this base times this height, is going to be 2 pi r times h. So lateral area of a cylinder is 2 pi rh, and then to get the total surface area, we'll take the lateral area, 2 pi rh, plus we need to add the areas of these two bases. Well, they're both circles, and you find the area of a circle by taking pi r squared. So we're going to take 2 times pi r squared. Remember, we're multiplying by 2 because this cylinder has 2 bases. So let's take a look at an example where we're going to find the lateral area and total surface area of the cylinder. So starting with lateral area, remember the formula for the lateral area of a cylinder is 2 pi rh, the circumference of the base times the height. So first of all, notice that what we're given in this picture is we're given not the radius of the base, but we're given the diameter of the base. So the diameter obviously is half of that, the radius is half of that diameter. So this radius is 7.5 millimeters. Okay, so in our formula, when we take we take 2 times pi times the radius times height, that's going to be 2 times pi times our radius is 7.5, and then the height of the prism is the distance from one base to another. So we can see that those bases are 18 millimeters apart. So that's 18, I'm not going to put the millimeters in until the end. Okay, so now let's multiply and simplify a bit. And so our final answer is going to be, and we're just going to leave this in terms of pi in the absence of directions otherwise. Let's just leave the answer exact and in terms of pi. But let's not forget our units. Since this is surface area, it's going to be millimeters squared. Okay, so there's our lateral area. So now let's find the total surface area, which would be that lateral area, 2 pi rh, plus the area of the two bases. So we've already done this work, 2 pi rh. We don't need to do it again. It's 270 pi. So it's going to be 270 pi plus 2 times pi times that radius of 7.5 squared. And then simplifying a bit, we would square the 7.5 and double it, and then combine with this term, and our final answer is going to be 382.5 pi millimeters squared. So now let's switch gears and start talking about three-dimensional figures that just have one base. We're going to talk about pyramids, and we're going to talk about cones. So let's first talk about a right pyramid. So a right pyramid is only going to have one base, and that base can be the shape of any polygon. So it's going to have one base, and then it's going to have lateral faces that are in the shape of a triangle. So triangular lateral faces. So if you take a look at this right pyramid, here's the net of the pyramid, which is just a two-dimensional representation of it. You can see the one base in this case is a pentagon, and there's going to be 1, 2, 3, 4, 5 lateral faces, and each one of them is in the shape of a triangle. So let's talk about how to find the lateral area and surface area of a pyramid. By the way, you might want to be familiar with all of these vocabulary terms. The vertex of a pyramid, the base is the one shape that's going to be a polygon. Lateral faces are all going to be a triangle. The altitude of a pyramid would be a segment that goes from vertex to the center of the base, and then this segment that goes from vertex to an edge, that's called the slant height, and that will be important here in just a minute. Okay, the slant height on this three-dimensional shape, you can see on the net that the slant height of the pyramid is also the altitude of one of those triangular faces. So let's talk about how to find the lateral area and surface area of a right pyramid. So let's start with lateral area. So you'll notice that every one of these lateral faces is a triangle with a base of S and an altitude of L. So how do we find the area of this one triangle? We would take 1/2 its base times its height. So the lateral area is going to be 1/2 S times L. That's for one of those triangular faces, plus 1/2 S times L. That would be a second one. And we're going to do this a total of 5 times because there are 5 triangular faces, each of which has a base of L and a height base of S and a height of L. So now what I'm going to do next is notice each one of these has a 1/2 L in common. I'm going to pull that 1/2 L out. I'm going to factor it out. So when I do, I'd be left with S plus S plus S plus S plus S. Well, looking at our picture, S plus S plus S plus S plus S is also the perimeter of the base. So in other words, to find the lateral area of a pyramid, we just take 1/2 capital P times L, where capital P is the perimeter of the base and L is the slant height. So let's go ahead and fill it in down here, 1/2 capital P times L. And then to find the total surface area, all we need to add to that is the area of the one base. So we will write the total surface area formula like this, 1/2 P times L plus capital B, where remember capital B represents the area of the base. So let's take a look at a couple of examples. This first one we have, find the lateral area and total surface area of a square pyramid. So that means it's a pyramid whose base is a square. So let's start with the formula. So the formula for lateral area is 1/2 capital P times L, where P is the perimeter of the base and L is what we call the slant height. So as we start to fill in this formula, we know what the perimeter is. Since the base is a square, then the perimeter is going to be 12 plus 12 plus 12 plus 12, which is 48. Okay, but to find the lateral area, we're going to have to do a little bit of work. So what I want to point out is this triangle right here. Let me redraw that triangle. It's going to be a right triangle. Its hypotenuse is L. The altitude of this side of the triangle is the altitude of the pyramid, so that's going to be 16. And then this side of the triangle, notice we go from the center of the base to the edge, so don't put 12. 12 is the entire edge, so from the center to the edge is just going to be 6 centimeters long. So this is a triangle that has 2 legs, 6 and 16. And so to find the slant height, we'll just use Pythagorean theorem, which says the hypotenuse squared is equal to the sum of the squares of the 2 legs. So L squared is equal to, let's see, 256 plus 36. I'm sorry, you can't read that. That's a 6. And then that means L squared is equal to 292. So L is equal to the square root of 292. Now we could simplify that, but for now, let's just leave it square root of 292. So that means our lateral, that should be 2. Our lateral area, once we put units on, would be 1/2. Oh, I guess we could simplify this a little bit. Let's call it 24 times the square root of 292, and then put our units of centimeters squared on there. Okay, so that's lateral area. So then total surface area, we're going to take the lateral area and then the area of that one base. So we've already done the work for 1/2 PL. We know it's this, 24 times the square root of 292. Which I know that could be simplified a little bit, but for now we're not going to worry about it. And then let's add that to the area of the base. Well, the base is a square. Oops. The base is a square, and we find the area of a square just by taking one edge and squaring it. So that would be plus 12 squared. So final answer is 24 times the square root of 292 plus 144. Let's put parentheses around all of that and then put the proper units, which would be centimeters squared. okay? And then this time, let's find the lateral area and total surface area of a regular hexagonal pyramid, which means its base is a regular hexagon. So, starting with lateral area is 1/2 capital P times L. That's 1/2 the perimeter of the base. Well, the perimeter of the base, it's a regular hexagon, so we just take 5 and multiply it by 6 to get the perimeter. So that would be 1/2 times 30 times the slant height. This time we don't have to figure out the slant height. We're given the slant height to be 8. Okay, and then we can simplify that a little bit. 15 times 8 is 120 centimeters squared. Okay, so now to find the total surface area, we're going to take the lateral area and then add to that the one base. Well, again, we've already done this work. We know what 1/2 PL is. It's 120. So that's going to be 120 plus the area of the base. Well, what is the base? The base is a regular hexagon. So I'm going to go ahead and draw just a bird's eye view of that base. Or I'm going to attempt to draw a regular hexagon. And remember, we find the area of a regular polygon by taking 1/2 its apothem times its perimeter. So I'm going to go ahead and draw an apothem. And then I'm also going to draw a radius to create a little right triangle for us to work with. So what do we know? We know this side of that triangle because remember when we drew the apothem, we drew it to the midpoint of a side. The whole side is 5, so this piece would be 2.5. So I'm going to label that, okay? And then to find A, to find our apothem, let's see if we can figure out what this angle is. Well, since this is a hexagon, if I were to draw all of the central angles, there would be 6 of them. And so 360 divided by 6 is 60. So this central angle is 60 degrees, but I drew the apothem, which bisected it, which makes this angle 30 degrees. So that means this little right triangle we're looking at is a 30, 60, 90, where I know the short leg, and I want to know the long leg, which also happens to be the apothem of the base of my pyramid. So if I know the short leg and I want to find the long leg in a 30, 60, 90, we just take that short leg and we multiply it by the square root of 3. So the area of this hexagonal base is going to be 1/2 times the apothem, which is going to be 2.5 times the square root of 3. So 2.5 times the square root of 3, and then times the perimeter of the base. Well, the perimeter of the base is going to be 30. Remember, each edge measured 5, and there's 6 of them, so that is times 30. Okay, so we can simplify that a little bit. Let's see, half of 30 is 15, and 15 times 2.5. See, this is 37.5 times the square root of 3. Okay, so we did all that work to get the area of the base, because remember we were trying to find total surface area, and so now I have found the area of my base. The area of my base is 37.5 times the square root of 3. So I'm going to write my final answer, 37.5 times the square root of 3. Let's put parentheses around all that and put the proper units, which would be centimeters squared. So now let's take a look at our last three-dimensional shape, a right cone. So a right cone, like a pyramid, only has one base, but if it's a cone, that base will always be a circle. A pyramid can have a base that's any polygon, but a cone will always have the same base. It's going to be a circle. So that means a right cone has one circular base, okay, and then it has a vertex, and then it's got this curved lateral surface. You'll also notice that the slant height of a cone is similar to the slant height of a pyramid. One endpoint will be at the vertex, the other endpoint will be on the actual edge of the base. All right? So let's talk about how to derive a formula for the lateral area and the surface area of a cone. So I want you to take a look at this net of a cone. Okay, if you were to take a cone and lay it out flat, it has kind of an unusual shape. This is the lateral area. This is that curved surface area. But notice once you lay it out flat, it doesn't make a complete circle, which you might have expected. It makes kind of this Pac-Man type shape. It's part of a circle. So to find a formula for the lateral area, what we're going to do is we're going to compare the area of this blue part to the area of an entire circle, we're going to take that ratio and compare it to the circumference of this blue shape to the circumference of the entire circle. So let's write that out, what I just said. So we're going to write a proportion that compares the lateral area, that blue lateral area, to the area of a complete circle that has a radius of L. Notice that if we were to complete this circle, its radius would be L, which would, if you put the cone back together, L is the slant height of the cone. So area of a complete circle that has radius L, and then we're going to compare that ratio to the measure of the arc, and the arc, say measure of the arc. Now the arc that I'm talking about is this arc. It's the distance around this lateral area, okay? So the measure of the arc to the measure of the circumference of the entire circle. So circumference of the entire circle with radius L, okay? So once again, here's what our proportion compares. It compares this blue area to the blue area of this entire circle. Okay, we'll take that ratio and set it equal to this partial circumference to the circumference to the total circle. So what that would look like, well, we're just going to call lateral area LA. Now, the area of this complete circle would be pi times its radius squared. So that's pi times L squared, okay? And then that's equal to the measure of this arc. Now this arc, notice if we were to put this cone back together, then from here to here is the same thing as the circumference of the base, where the base has a radius of r. So the measure of this arc is going to be 2 pi r. And then we're going to put that over the circumference of the entire circle with radius L. This entire circumference would be 2 times pi times its radius, which is L. So 2 times pi times L. Okay, so now if we can at this point, notice there's a common factor of 2 pi that we can cancel, okay? So now we're going to cross multiply, and I'm going to run out of room, so I'm going to move the work down here. When we cross multiply, then I would have LA times L, that's what I get when I cross multiply this way, is equal to, when I cross multiply this way, I'd have 2 times pi times, I'm sorry, the 2 pi's gone. When I cross multiply this way, I'd have pi times r times L squared. So pi times r times L squared. Now we can cancel an r from both sides, I mean not an r, an L from both sides, okay? So all that to say that lateral area is equal to pi times the radius times the slant height, okay? So if you didn't follow all of that, that's okay. I just wanted you to know that this formula doesn't come out of nowhere, okay? What you need to know is you need to know the formula. Lateral area of a cone is pi times the radius of the base times the slant height of the cone. And then so then total surface area is going to be that lateral area, pi RL, plus the area of the one base, which is a circle, and the way we find the area of a circle with radius r is pi r squared. Okay, so let's finish up with an example. Let's find the lateral area and total surface area of a cone. Okay, so lateral area and total surface area. Okay, so let's start with the lateral area. So the formula for the lateral area is pi times r times L. So that's going to be pi times the radius of the base, which is 6, okay? And then we need to multiply that by the slant height, which I'm going to label the slant height L. We don't know that slant height, so let's go ahead and use this little right triangle and the Pythagorean theorem to find out what L is. So L, which is our hypotenuse squared, is equal to the sum of the squares of the two legs. That would be 7 squared plus 6 squared. So L squared equals 49 plus 36. L squared equals L squared equals 85, so that means L is equal to the square root of 85. Okay, so we'll put that into the formula. Okay, and I'm just going to rewrite this a little bit. The lateral area of this cone would be 6 times pi times the square root of 85. And then let's put units on that. That would be inches squared. So then to find total surface area, we will take pi RL plus the area of the one circle, pi r squared. We've already done pi RL. That was 6 times pi times the square root of 85. So let's multiply that by the area of this base with radius 6. So that's going to be pi times 6 squared. Or final answer, we'll just write 6 pi times the square root of 85 plus 36 pi. Let's put parentheses around all that and put the proper unit of inches squared. All right, so there's lateral area and surface area of this last example. All right, so I hope you don't have any questions, but if you do, be sure and ask me in class, and we'll be getting some more practice in class as we work on some practice problems, and I will see you then.